and thank you for coming, despite the fall rate. I'll be talking about homomorphism testing, a general-ish framework to do this, and a bunch of results. This joint work with Shaurya at the University of Ireland. Yes, the outline is as follows. I'll introduce the problem and motivate how this problem comes about to be, and then I'll define exactly the precise problem of homomorphism testing, state this general framework, and then the precise results I get. Okay, so let's get started with the most basic things, a linear function. Right? So if I ask you what a linear function is, the image that you'd probably think of is this. So if you think of a function from the real store itself, then this is what you might think of as a linear function. Or if you're more into equations, you might think of a more analytic degree 1 equation. So a linear function can be represented in this form. Or more generally, you can say a linear function is something that satisfies the functional equation. f of x plus y, f of x plus y. So you kind of understand what a linear function is. But now if I ask you what an approximately linear function is, then there's probably no canonical way to think about it. Right? You can probably try to define it in multiple ways with multiple goals in mind. But why would we want to do it? Like, why would we care about doing such a thing? From a complexity theory perspective, it's hard to check exact linearity. If I told you that, check whether a function is linear, you probably have to look at it at every point. That's not efficient. So we want a notion that's more efficient. Or from a coding theorist perspective, you will never have exact structure. Right? Even if you start off with things that are maybe perfectly linear, then there's a noise in your system, so you have to deal with things that are approximately structured and not exactly. And broadly, even from a math perspective, you want robust definitions. You want definitions that are not brittle, that don't change, like for example, linearity, even if I change the function value at one point, it's no longer linear. Right? But you probably want to say interesting things about even such functions. Okay, so that's the motivation we're coming from, and the kind of notion that we're looking for. We need two properties. One is algorithmic efficiency, like I said. We want a property, a notion of approximation that is efficiently checkable. And it's useful in the sense that it's a notion of approximation that lets us prove worst case bounds. Right? So we want both these properties. Right? And this kind of a thing is motivated by our PCPs. Right? The reason why we consider such a definition. So, this line of work on interactive proofs, connections to harness approximation. So there one of the components of these PCP theorems is this notion of approximate linearity, or more generally approximate low degree functions. So classically, people have studied this for linear functions, and the generalizations to the quantum interactive proofs require more general notions of homomorphisms. So between proofs that are not necessarily, you can think of that as like additive. Okay. So if you haven't seen a PCP, that's what it looks like. It's a very nice illustration that I like from Quanta, Christina. So you think of the huge bit string that's hiding behind this wall as your large proof, and it's so large that you cannot see all of it. So your computationally bounded verifier can only lean at 3 bits at a time, let's say. So this is what you must think of as this proof. And let me formally define it. I won't need the definition, but this will motivate the definition of the testing. Right? So I'll refer to the definition. So a PCP verifier is an algorithm that reads these 3 times k bits. Think of k as any parameter, and it makes a decision. Okay, is this proof correct or not? That's what it's trying to check. So it reads a few bits, makes a decision. And what are the properties? Well, if the proof was correct, it must say yes. Right? It must not reject correct proofs. Okay. But on the other hand, it might accept wrong proofs because it's only reading few bits. But it won't do that with a lot of chunks. Right? So it only accepts wrong proof with probably at most 2 to the negative k. So as you read more and more bits, you're more confident that the proof is correct. And of course, the landmark result is that for every NP verified, you can make it a PCP with just a polynomial law. Okay. So yeah, so this is the kind of result that sitting inside the PCP, like this entire machinery of converting a proof to PCP, one of the key components is this linearity test. Okay. So now let's define this problem. So we'll be talking about groups throughout the thing. A group is just a set with a binary operation that can be input. So you have an inverse and you have binary operation. Two very canonical groups that you keep in mind are the cyclic group. So this is a group of integers modulo a number n, and the group operation is just addition mod n. Okay, so for n equals 8, that's what it will look like. So the set is the set 0 through 7, and addition is modulo 8. And clearly that can be inverted, you just take minus x. So that's the next one. Another example that CS people like is the hypercube, right? So the product group ZP to n, where so this as a set, it is n tuples of numbers where each entry is from 0 to p minus 1. The group operation is addition in each coordinate modulo the number. So, favorite hypercube. So again, notice if you haven't seen the groups much before, as sets these are bijective. There's a very natural bijection from integers through 8 through 3-bit strings. You can just encode it by the binary representation. But that's not a group isomorphism. So that bijection would not preserve group structure. Right? So in fact, as groups, there is no isomorphism. They're very different as groups. But as sets, they're the same. Okay. So yeah, throughout the talk, all groups will be finite. And as long as this is clear, it should be fine. Okay, so what's a group homomorphism? Now that the set has more structure, a homomorphism is a map that respects the structure. Okay. What do I mean? Take a pair of groups. So a map is a homomorphism if for every pair of points, it doesn't matter whether you do the group operation first or apply the map first. So f of x times y. So this operation is the group operation in G. Is same as you apply the map and then apply the group operation in H. So although the notation is same, they might be very different operations. Okay. So again, going back to the linearity example, if G and H you think of as R, so the real numbers is a group under addition. So this is just f of x plus y is f of x plus f of y. So that's linearity. This is generalizes the notion of linearity. Okay, so just to make sure everyone's on the same page, so think of a map from the cyclic group itself. So what does it mean for it to be a homomorphism? Well, for any number I here, I can write I as 1 plus 1 plus 1 I times. By this property, it just means that this should be equal to f of 1 plus f of 1 plus f of 1 I times. Right? So what this constraint, this homomorphism constraint tells you is that the function is determined by its value at 1. So once you tell me what f of 1 is, the function is determined. So clearly it's a much smaller class of functions. An arbitrary function would have much more freedom. So yeah, if f of 1 was 3, then f of 0 has to be 0, f of 2 would be 6, f of 3 would be 9, which is 1 to 8, and so on. Right? Okay with groups and homomorphism. Alright, so what's a homomorphism test? A k-query test looks at k points, right? So think of, again, instead of the proof, the huge proof, think of that as being the values of f of x at different points x, right? You look at k of those points. So you get k function values. And then you make a decision whether this function is a homomorphism or not. Right? That's what you want to decide now. Again, as before, if f is a genuine homomorphism, then you always want to accept. You don't want to reject true homomorphisms. Right? And likewise, if you do accept this homomorphism, so there is a chance that this could be wrong, right? Because you haven't looked at the function. But if you output yes with probability delta, so this is over your choice of random bits here, your random points that you're querying at, right? So over this chance, if you're accepting a function f with probability delta, then this function must have something to do with a true homomorphism. And this notion of closeness is in this Hamming distance. So there should be a fraction of point which is a function of this delta. So at s of delta many fraction of points, your function must agree with a true homomorphism. That's the guarantee that you. So this is the mathematically useful part of the statement, and this is the efficiency part of the. Okay. So pictorially, what's happening? You have this entire space of functions between any pairs of groups. Just forget the group structure. Then you have the homomorphisms which respect the group structure. And once you define such a test, you get a notion of approximate homomorphism. Right? So these are all functions that pass your test with probability delta. Okay. By the completeness, you know that it at least includes all the true homomorphisms. So this is a strict subset of this. And the soundness guarantee tells you that these approximate ones are not too far. So anything in this set is not too far from a true homomorphism. And so this is pictorially what, once you get a test with all those guarantees, this is what you get. The upshot now, by enlarging the set, is that this larger set is efficiently testable. This original set you could not test with just k points, but the larger one you can test with k points, just k queries. Okay, so that's okay. So what's known? Right? So the most classic result is the BLR. The 90s, which started, I guess, all of property testing. So Bloom, Luby, and Rubenfeld gave the most natural test that you can think of. So they say, okay, pick a random x, pick a random y, and then check whether f of x times f of y is f of x. Basically, check the definition of it being a homomorphism. Right? So now, what is the so now given this test, what is this test passing probability? That's just the fraction of pairs for which this equation holds. Right? So if delta is 1, that is equivalent to the function being a homomorphism. Right? It's just a restatement of the function being homomorphism. But the question is, if delta is 0.7, what does that mean? The f having structure. If delta is 0.01, so that's just a constant for a function f. Now you want to deduce some structural property. Namely, what we want is that it is close to a true homomorphism. So once I tell you this number for a given function f, can you guarantee that there is a homomorphism phi that is close to my function? Ideally, you want this thing to not depend on your group g and h. Right? You just want this to be a function of delta. It shouldn't have factors of g and h in it. Okay. The nice thing about the BLR test is it's just well defined for any pair of groups. Right? This definition has assumed nothing about the group and so on. It just makes sense for any pair. Okay. So now what's known can be divided into two regimes, the high soundness and the low soundness. So the high soundness is when you give me such a guarantee, a soundness guarantee, but only if delta is large. Right? So say delta is at least 7 over 9, you tell me such a claim that yes, that is a homomorphism. If delta is smaller than 7 over 9, you give up. You make no claims about the function. Okay, so clearly that's a restriction. So that's an easy case. And there we kind of have a nice picture. So for any pair of finite groups, we have such a guarantee that yes, there indeed exists a homomorphism. And the coding theorists call it a unique decoding regime. This is because when your delta is that large, right? So you're kind of very close to being a homomorphism. So then this homomorphism is first of all unique. There's only one homomorphism that's very close to your function. And that one homomorphism is constructed via this majority decoding procedure. It's like a very simple definition. It is just I mean, you don't need the definition, but it's just about it. This is the majority of f of x. So look at the entire orbit, right? So look at all elements G, and f of xg times f of g groups. So if f were a true homomorphism, then this would cancel out and this would be just supported on one element. It's not a homomorphism, but there'll be a spike in the case when delta is large. So essentially, this construction gives you for any pair of finite groups. I mean, the proof takes a bit of work.
So what do you mean when you say, like, how's the high soundness? I guess I just don't understand the level path.
Oh, so I mean that you're only giving me this guarantee that there is a homomorphism that is close, assuming delta is very large.
What guarantee? What is being guaranteed here?
the guaranteed is that this function phi is a genuine homomorphism. That's the first claim.
Sorry, that's what you're trying to prove.
What?
You're trying to prove that. You're constructing some phi.
Yes, yes. So the claim there is that there is a phi that is close to your function.
Okay.
Right? But this proof is assuming that this delta is large. That's the only difference.
Okay.
So this construction of phi only works if delta was large.
Right.
If delta was 0.01, then this is not a homomorphism.
Right, sure.
Okay. Alright, and then we also have de-randomized tests in this regime and extensions to non-finite pools and so on. Okay, and that's why this is the unique decoding regime from the coding perspective. Right? The other hand, the low soundness, you don't have any assumption on that. Right? Maybe that is just better than random. So it's like 1 by h. Right? So 1 by the size of the target would be like a random test passing probability, you just have something more than that. Okay, so what do we know? We know very little in this regime. The classical result is the one for hypercube, so Z2 to the n to Z2, which says that if you test, the BLR test passes with probability delta, then there is a function that agrees on delta fraction points. So in some sense, this is like the optimal thing that we want. As delta goes to 1, this smoothly goes to 1. The extension to ZP was done by Haas and Peterson, but there was this loss that is not great. Right, so for any P, they got this kind of a result. Okay, so delta passing implies 1 over delta by P, agreed.
It's an improvement for P equals 2, right?
Not really, I mean, okay, so this is an approximation that I wrote. So actually here it should be half plus.
Oh, okay.
I mean so 1 by P is like a trivial agreement that you'll have. So you should actually ignore this 1 over P.
Okay.
Yeah. Okay. So, and then the other set of results that we know is for Z2 to the n to Z2 to the m. So here think of m as large, maybe m is n. So Soundess first showed that there's an inverse exponential soundness guarantee using connections to additive combinatorics, right? And making this polynomial is equivalent to the polynomial Feynman-Rujah conjecture, which is now here. So they're equivalent statements, whether you have the PFR. So Sanders made this quasi-poly, and then recently you have polynomial sound. Okay. So this is kind of what clearly you see a stark difference, right? I mean, here we know it for every pair of groups, and here we just know it for three. And this is the called the list decoding setup, because you're not going to be close to a single homomorphism field like that. You might have tiny agreement with a lot of different homomorphisms.
This last result also for like ZP for like constant P, or?
Yeah, I think for constant P, yes. For constant P, but yeah, this thing there are like a lot of factors of P here. Okay, so I mean, one issue is that this we have it for very few groups. The other thing, like I mentioned, we have this agreement is not quite what we want. Right? So when P is large, you don't get much, even if your test passing was close to 1. And the key issue is that BLR actually as a test does not work. Right? It's again not the fact that people haven't analyzed it for other groups. The test is too weak to work in the low soundness regime, although it works in the high soundness regime. Right? So in the original paper itself, Coppersmith gave a counterexample wherein he showed that for every k, there is a function mapping from z mod 3 to the k to z mod 3 to the k minus 1, which really passes the test with high probability, 7 over 9. But the function has nothing to do with any homomorphism. It only agrees with the homomorphism at 3 points out of 3 to the k points. So it's like terrible. The other answer as a function. Yeah.
Sorry, in that first one, when you set delta to 1, isn't that just the high soundness region?
Yeah, but then it's kind of like that result. I mean, okay, let's think of delta is 7 over 9 or something, right? You're getting vanishing
on the
list.
border. Okay.
Yeah. I mean, of course, if delta is 1, then you're saying you could switch to the other result and prove it. But yeah, like that result, yeah, think of it at the bottom. Right, so this is just showing that BLR will not work, even for cyclic groups. Okay. So the first one was actually corrected by Kiwi. So Kiwi gave a variation of the BLR for the ZP case and got rid of this factor. Okay, but that's more or less what we have in terms of homomorphism tests. We have the VLR for those and the Kiwi variation of the VLR. Okay, so what we would like is if you give me a pair of groups, any general group, even cyclic groups, how do I design a test? Right? The one test that I know does not seem to work. How do I analyze them? So most of the all of the previous results used for analysis, right? They embed H into complexes via, like for Z2 you can actually do it. Even for ZP you can think of it as a unit circle. You can do for analysis, but we don't have other tools to analyze tests in the low soundness regime. In the high soundness, there's like a combinatorial proof for this. But in the low soundness, the combinatorial techniques are not good enough to get you a result. But in general, for general group H, you might not be able to easily use Fourier analysis to do these things. And then you would like a test that can trade off queries for soundness. So just like we saw in PCP, right? The higher K you make, the better guarantee you get. So you want that kind of flexibility. Okay. So just a summary of what is to come. So what is known, we've seen are these three cases. Again, primes, you can make prime powers, I'm not going to. And what we show are a bunch of new tests. So they cover this family. So they don't cover the PFR case. They can do the cyclic group, which as you saw VLR cannot do. So this is between an arbitrary pair of cyclic groups. So in particular for the counter example, 3 to the k, 3 to the k minus 1. And a bunch of other groups. So these are like the one-dimensional representations of n by n invertible matrices over FQ. And some non-abelian groups. So clearly, like the known results, we only have abelian families of abelian groups, and we get results for non-abelian groups, including, I'll explain in detail, but like inner automorphisms of all finite simple groups, or more generally quasi-random groups. Okay, so basically, we have a bunch of tests, but all of them come from sort of a unified framework to generate these tests. Right? That's what I talk about. Okay, so just to motivate what's different and what's happening, let's look at the toy case where you have a function from ZP squared to ZP squared, right? The cyclic case for which BLR goes. And let's say I give you guarantee that either f is purely random, by which I am going to assign f of 0 to be 0, and f of x to be just some random number from 0 to p square minus 1. Right? So either f is generated via this process, or it's some genuine homomorphism. Let's say I give you this guarantee, there's nothing in between. And I only ask you to make one query and place your bets, right? Like you get one query and then you put money on one of the sides. So now you have like p square options, right? So you have p square points in this group. I mean, f of 0 you don't care about, I guess. 0 is already defined. So f p square minus 1 possible queries you could make. Which one would you make?
Choose something that's divisible by p.
Okay, so a multiple of p. Any other guesses?
You have to use that like p squared is not prime, otherwise you can't do anything.
I mean, this is. So what does a true homomorphism look like? So these are the p square points. We have special points 0, 1 and multiples of p. We did see that for cyclic groups, the homomorphism is fixed by just the value at 1. Once I tell you that phi of 1 is I know phi of x for any x. It's just I times that module of p squared. Okay, so now I can fix phi of 1 to be any I. Doesn't matter. But what this would force me is that the value of any multiple of p will remain a multiple of p. Right? That's what this would give me. If I plug in x to be some multiple of p. Right? So now there's a constraint. So when you look at the function values of multiples of p, there is some constraint that a homomorphism tells you. But if you just look at f of 1, there is no constraint. So if you query this function at f of 1, you get nothing. You learn nothing about the function. But if you query it at f of p, there's a chance that you might detect Because if it were not truly at random, with high chance it's not going to be multiple. Yeah, makes sense? Right, so this is what I'm trying to convey. That the elements of your group are not giving you the same information. It's not that every element of the group is giving you the same information about being the property of being homomorphic. Right? And this is exactly what the Wheeler does not use. Again, the Wheeler test is sample a uniform X, sample a uniform Y, test it. It doesn't care about G, doesn't care about H, doesn't care about the structure of homomorphisms between G and H. Right? So in this group, if you sampled a uniformly random element, you would probably not hit a multiple of P. Right? And then you'll also not learn much. But that's one intuitive explanation for why Wheeler is failing for cycle groups. Okay, so the takeaway is that we need a custom kind of distribution on GTK that uses the group structure, that uses the structure of homomorphism. Right? So to deduce this information, we used what a homomorphism looks like between cyclic groups. We use that data to make this choice. But if I change the target group H, then again this would change. Right? Okay, so how do we come up with this distribution? Okay, so the key thing is actually to work backwards. Right? So instead of coming up with a distribution, let's start with what do we want. Well, we want a test, some test, a low query test, such that this quantity, the max over all the agreements, is at least some function of this test passing problem. That's what we want. Right? If we had this, we had the soundness guarantee. Right? Again, always max is hard to work with. So we'd be okay if we get something like this. If we can say that the kth moment of this vector of agreements with all possible homomorphisms is proportional to some test passing problem. So we're going to shoot for this more approachable goal. Yeah.
What's test sub k?
So this is, think of a k query test. Like this, or yeah, like if you want k, I mean, if you change k, the same test will not give you all the moments, right? So whatever is needed to get this. Okay. So the goal is to try to get something that sort of approximates this. Again, if you've seen it for the hypercube, the Wheeler test kind of has f hat cube, the Fourier coefficient cube, and this is the agreement is kind of like the Fourier coefficient, half plus the. Okay, so the key way to do this is this kind of an expression. So to define that, fix any tuple of elements in G to the K. So first fix this. So this is some elements from G to the K. And define the map gamma x, which maps homomorphisms to H to the K. And it's a very natural map. It just evaluates homomorphisms. So once you fix the tuple x1 through xk, this map is defined. And it's defined as follows. You just take a function or a homomorphism phi, evaluate it at the K points. Okay, so for any tuple x, this is a map. This is in fact a homomorphism between these groups. And that is used in the proof. But the key lemma that you get with a little bit of work is that this moment has an exact expression in terms of this map gamma. So this kth vector of this k naught is the expectation over all tuples. You look at the map gamma, the kernel of this map times the indicator whether. So this means that f of x1, comma f of x2, comma f of xk, that vector is in this image of this map. So it's an indicator function for that. Is the statement clear? Right. So for any tuple, fix a tuple, you get a map gamma x. That's the size of the kernel, and this is just an indicator whether f of x lies in the image. So f of x lying in the image is basically same as saying f agrees with some phi on these k points.
Why are we multiplying by the size of the kernel?
I mean, that's kind of what you get, because the thing is the kernel of gamma controls how many, like the multiplicity with which you get this kind of quantity. So Yeah, I mean this is, you wouldn't need this for the equality to hold. So, but now when you stare at this, you kind of get a test. If you stare at the right hand side and you interpret this as a test, what it says is that you sample an element with this weight, the kernel of gamma x weight, and then check this condition. That's what this says as a test. You can just interpret it that way. If you do that, once you take the normalization constant out, this is what you get. And this is just sum over all x gamma x, which is just a pure kernel gamma x, sorry. And that's just a constant depending on the group. So once you have this expression, you can read off the test from this.
Pretty well, interesting. Got pretty query at one of these points. Like you go over all homomorphisms and check whether
Technically, yes.
F could be this homomorphism. You can't do this some way.
Yes, but for most of the groups, for the natural kind of groups you can study, you can give an alternate description of this in a much more.
Yeah, I'm not worried about
Yeah.
The efficiency per se. Just
Yeah, but that is a test. Yeah.
Yeah, okay, yeah. Feel for the test.
So I'll define the test again. Yeah, question.
How large does K need to be? Because you wanted the max, but here you only have the Kth element.
Very good. I will talk about it.
Okay.
That will determine the query complexity of the test. Okay. So the test is as follows: you sample a tuple from this distribution, and then you check this entire vector and check if it's in this image. Okay. Now, look. So this is again a general recipe, right? I mean, this thing is defined for a pair of groups G and H, at least for abelian groups. This is very defined. The only thing is that so this is also a distribution that takes into account the group structure, because that's what gamma does. So in some sense, kernel gamma x takes into account the structure of the homomorphisms. So unlike VLR, like, it's kind of a general definition, but it is not the uniform distribution for all groups. It's kind of a custom distribution. Yeah, just to unpack what this size is, it's just the number of homomorphisms phi that vanish on all k points. Okay. So I mean, if you think of a subspace, right? If all the k points lie in a low-dimensional subspace, then more things will be zero there, as opposed to if they were random. So just to like give an intuition as to why this deviating makes sense, I guess what you asked. So again, going back to the ZP square case, if I just think of k equals 1, I'm just looking at a single element, then this size is purely determined by whether it's a multiple of p or not. So if it were a multiple of p, then this thing gets a factor p, right? Because the number of homomorphisms that are going to be 0 is if phi of 1 is fixed to be any multiple of p, then phi of alpha p will be alpha p square, which will be 0. Otherwise, it's 1.
You said before that there's like you're not getting anything if you sample the non-morphism piece. So is it useful to have the 1 there in the sample probability?
Yeah. So I mean, the thing is, ideally, you don't even want to look at the other elements.
Yeah.
I mean, for k equal to 1, the thing is k equal to 1 won't give you a test, but this thing at least significantly balances it out, right?
Yeah.
So if you sample from this distribution, at least you'll probably half now you get multiples of p
Yeah.
instead of vanishingly small. And then of course you could also remove the other elements. But those elements are still useful when you have k larger.
Mm-hmm.
So let's say you have f of 1 and f of 3 and f of 7. There might not be multiples of p, but there is still a constraint that f of 3 must be 3 times f of 1. So sampling them is not useless in the k larger region.
Sure.
Okay. So is the test clear? What the test is, and why this kind of makes sense?
So, is the BLR test over F2 to the N a special case of this?
Yes. So I mean, actually, when we apply this to the BLR, we kind of recover because BLR will only sample things that are like x, y, x plus y, and most of the weight. Again, there will be some smaller, very exponentially small weight elements, but up to 2 to the minus n kind of errors, this would recover BLR for 3 to the n to the n. Okay, so the analysis is very simple because that's how we came up with the test. So the key thing is as follows. The test is well defined for any pair of groups. All you have to do is sit down and bound this number. And this is where your question about smallest k comes in. This number could be large for some k, but as k increases, you might get a better handle on this. the analysis is just, once you have the kth moments, it's nothing, right? It's you just have this kind of ratio. Each of these moments you know is gamma k times something, and gamma k minus 1 times some number which is less than 1, at most 1. It's a test passing probability of the k minus 1 at test.
So you missing something in John Peter? We should divide by.
Yes, so here you will have the test passing probability of the k minus 1 query test.
So you just didn't put that on the slide.
Yeah, no, that's at least at most 1.
But you put equality.
Oh yeah, there should be an inequality, sorry.
Oh, okay. Oh,
Sorry.
okay.
Inequality, yep. Yeah, I think I made that edit later. Okay, so what you have is, you have a soundness like statement, right? You have the test passing, you have the sound, like the closeness guarantee is proportional to the test passing probability. And this is the constant. So as long as gamma k by gamma k minus 1 is a true constant, it's not something like order g or g square or g something, then you're good. So you need the smallest k for which this ratio is a constant, absolute constant. And of course, you can do other things. So this vanilla approximation might not work. So you might want to threshold. So you might have a lot of small noisy homomorphisms. So you might want to threshold away those with some tau. And then you can expand this out using this binomial and then apply this. Or, like you said for the cyclic group, right? You might want to subsample a distribution. Like if you know for a fact certain elements are not that useful, you can define a subdistribution of this, of sort, like forbid some elements. But you can do this modifications, but this gives you like a good starting point to define the test. And this is how we get all the results, some modification for certain groups. Okay, so now let me tell you what the results are. Okay, is the framework and the analysis all that clear? Okay, so between pairs of abelian groups, we covered the result of Curie. So remember that for Hastad Wickerson, you had like a delta by p kind of a dependence. And now, so like I said, TV gave a modification of the Bela test that removes that, and this test, again, up to some small minute change in the distribution, it's very close to what Kiwi's test is, basically. So you also get again the same almost optimal parameters. So it's a 3-query test. More interestingly, you can get the Coppersmith counterexample. So between ZP to the R and ZP to the S for any P, R, and S. You get a 3-query test with almost delta. So this is the case for which BLR does not work. And then you can generalize this. You can make the target group any group as long as its P rank is small. So once you decompose the abelian group as sum of cyclic groups, the number of cyclic groups which have a power of P is at most T. So then you need a T plus 2 query test. So the upper case is when T is 1. So that generalizes that case. Okay? Then you can get it between any pair of cyclic groups. There's just one bump in the number of queries. This is the Riemann-Zeta function. This might, it's probably possible to make it 3. It's just that the analysis of this constant gamma becomes kind of hard. So yeah, this is an approximation that lets you do that. And then the inverse case of this, you get some. Again, all of this using the same framework. In each of these, you sit down, compute gamma, and then you try to modify either test a bit or the distribution a little bit to make sure it's work.
Last four results are rows are new.
Yes. Yeah, so except for this one, so this one covers both like Z2 and the ZP case. So all of these in. So except for this and the PFR, the only 2 cases we know are either this and the PFR case. They're the only 2 settings for which we have Hamming distance kind of bound, and the rest all are new results.
So is this true if you take direct products of groups? Would these results generalize to that?
Not directly. They do for list decoding bounds, but for testing that's not true. Yeah.
So I noticed that on the G column, it seems to only have single cyclic groups. I was wondering if you had any results about products of cyclic groups.
I'll tell you something. But yeah, it's not like you can directly do it, but I'll just explain. Okay, so on the non-abelian side, it's even hard to tell you what the homomorphisms are between a pair of finite groups G and H. Like for abelian groups, you have the structured theorem, but for an arbitrary pair, I can't even write down what the homomorphisms are, or like some description in general. Right? Again, for like fetch is unitaries, then that's representation theory and so on, right? But apart from special cases, we don't know much. But one family we definitely know are inner automorphisms. So for any group G, fix an element little g, and look at this as a map. Right? This is conjugates. This is a homomorphism from G to itself, and is bijective. So these are what's called inner automorphisms. Right? So they are a subgroup of all automorphisms, which are all bijective maps. So we analyze this class of things. Again, here the test is not quite the kernel gamma, but it's very similar. It's like the stabilizer of this thing. So we get like for the full automorphism group, we get 3 query tests for diagonal group and the symmetric group. So for the symmetric group, the inner automorphisms and automorphisms are the same. Every automorphism is an inner automorphism. For the remaining families of groups, we get inner automorphism tests. So we get 4 query tests for every non-abelian finite simple group and any quasi-random group. So it's like polynomially quasi-random, which means that the smallest representation is, let's say, g to the constant dimension, and this family of extra special groups. So these generalize Heisenberg groups. If you've seen Heisenberg groups in, like, Pauli group and so on, the Weyl Heisenberg group, yeah, you've seen this in some quantum literature. So this family generalizes them. So there are P groups.
Just make sure this testing on the phi is like an inner automorphism or far from an inner automorphism.
Yes. Okay. And here something that I like is this constant gamma has been studied in very few papers, but there are some papers. So this constant that comes up is actually a very natural constant. It's the sum over all conjugacy classes. The size of the conjugacy class raised to 1 minus k. So now you think of this, and now you want to say how does this function decay? So this is some sort of a Riemann, like a zeta function associated with the group. And there's a paper of Liebeck and Schale where they call this like an analog of a zeta function, and they prove bounds on this. So basically the question of this testability reduces to how fast do functions like this on the group decay. So they truly depend on the group structure.
Would you like for a gamma defined vis-a-vis inner automorphism?
Yeah, so whatever, so this gamma was this normalization constant, right? Sum over the kernel of gamma x. Right? So I didn't tell you what the test for the non-abelian case was, but instead of, the kernel of gamma x will be kind of the stabilizers. So it will be some of the stabilizers. But yeah, exactly with this, whatever the normalization constant for the distribution is. Yeah, I mean, you could then plug in those bounds that you know. I mean, they use fancy machinery to do that. Or if you just assume the group is quasi-random, then you can compute this by hand. Because quasi-random groups don't have very large subgroups. That's bounded. You can compute, but then which groups are quasi-random, then you might again have to rely on known results. Okay, but that's all it depends on. Then you get the query versus soundness, right? The thing that we wanted for. So what I told you initially were the minimum number of queries. If you give me more, I get an improvement in the exponent. Just what we ideally want, right? This time the PCP. The more queries I do, I want better and better soundness. So again, recall the test is defined for any k, any g, and h. So it's an infinite family of tests for every k. Okay, so this is the same things that I mentioned before, but okay. The other nice feature is this thing lets you use algebraic like group homomorphisms. So let's say for some reason your homomorphism structure between a pair of rows G and H is same as that of A and B. Then you can reuse analysis. You don't have to do it again. You can use gamma of one to compute the gamma of the other, because these are also constants depending on the group structure and not. It's not like a combinatorial constant. Again, it's not a testing reduction. It's not like I'm using the tester for this to get to this. So the test is still defined by the kernel gamma x procedure. It's just that the analysis to compute gamma you can reuse stuff. Okay, and that lets you generalize results to groups where the homomorphisms factor. So something very simple is that if your target group is abelian, then no matter what G is, all the maps factor through its abelianization. Right? It's the abelian subgroup sitting inside the group. So, I mean, as a coding theorist, you can think of the big code as this code tensored with like repetition and so on. So, yeah, then you can basically use this to get tests for anything that factors through it. So, yeah, I'm not going to define, I guess I don't have enough time. to define what a Lie algebra is, but think of the canonical example you should think of is, so think of n by n matrices over FQ, and you want maps to FQ, right? So you can just think of them as groups under addition. So you want linearity, so f of A plus f of B should be f of A plus B, where A and B are matrices. But you additionally want that f of AB is same as f of BA. So that's the Lie algebra homomorphism condition. So think of this as like a trace map. Okay, so f of the commutator is 0. So this is, just a second. So this is a group homomorphism plus an extra condition. So this is what it means to be a Lie algebra homomorphism. So that's what is being tested for you. So you're testing the one-dimensional representation of this Lie algebra. But they correspond to just a group homomorphism sitting inside this Lie algebra, which is what is called a Scarpa subalgebra. So that's all that controls, because the target again is abelian. So it's like this is the abelianization version for algebras. Okay. But the point is you can also test for these structures without having to like redefine things and redo the analysis. Once you've done it for like prime powers or these kind of groups, sector groups. The same thing here. So these are again n by n matrices, and those are the invertible elements. So these are like the linear characters. Okay, yeah, your question. You had a question.
Oh no, it was these are stronger than just general group homomorphisms.
Yes, yes. So the group homomorphisms plus this extra. Okay, so this lifting lets you, hopefully you don't have to compute these things for every pair at the end. You can try to do it in a more modular way. Okay, and then finally you get list decoding bounds. So list decoding is like the inverse question. So testing says, guarantee that there's at least one function. And list decoding tells me, give me a bound, an upper bound on the total number of functions that are close. Right? Like I said, we are in the list decoding regime, so you're not close to one homomorphism, but many homomorphisms. So what the list decoding bound is to say that, okay, fix an epsilon. How many homomorphisms agree with my function at least epsilon fraction of points? So this is a combinatorial list decoding bound is just a bound on this. And the algorithmic question is to then output such functions, homomorphisms. Notice that our technique is actually bounding the kth moment, right? So using that you can get a trivial upper bound. So anything for which we have a test using this kind of a framework, you also have a list decoding bound, which is 1 over epsilon to the k, where you have a k plus 1 is the minimum number of queries of the test that you have, because that's the smallest gamma for which you could prove a constant bound. Okay, so as soon as the smallest k for which you can prove gamma is constant, you can get this list decoding bound. Right, so for example, for cyclic groups of like prime power, let's say, we get a bound of 1 over epsilon square, 2 over epsilon square. And this is much better than what was known. So the previous best result for these list decoding bounds were much larger, because they start off with ZP and they do a very combinatorial induction kind of thing. Their result, of course, is so they're focused on list decoding and they do it for all pairs of abelian groups, and there are also generalizations to solvable groups and so on. But that framework is dedicated to list decoding. It can't do testing. And in that framework, something that you just said, right? Like for direct product can be directly extended. So that is true in this setup. Because an upper bound for G1 and G2 implies an upper bound for G1 times G2. But that's not true for the lower bound, the testing. Okay. Yeah, so the point is that once you're getting much more than a testing result, you're getting a like kind of control on the moments. If you know what tolerant testing is, this also therefore all these tests are tolerant. Right? Because again, you have this upper and lower bound.
Natural is a coding theory problem when G and H are just some different cyclic groups. Like how I think about it, it's like the alphabet is like H, right? And like the code words are indexed by G.
Indexed by G, yes.
And it being a homomorphism is the notion of it being like a linear code.
It's not a linear code.
Yeah, but like it's like a homomorphism.
Yeah, so that's the homomorphism code, right? This is this set.
Yeah.
Yeah, I mean, I think the problem with these codes are that they're low rate, which is why they're not that well studied because, yeah, in terms of they have amazing distance.
Right.
The rate is bad. But yeah, I think there's this line of work where there are a couple of papers in this, and then also a paper of Latsi, Babai, and others studying this question for homomorphism codes, like the algorithmic aspects of the system. But I don't know many works that do it for cyclic groups. Okay, so essentially they're saying that all of this again you get for free once you bound gamma. There's nothing extra that's to be done here. So yeah, that's roughly what I had. So just to summarize what we saw like a general template to define this test coming from this kernel of gamma x, right? And it's a general enough template that it works for a wide variety of groups, but it's also custom. It's not uniform distribution. It's not general in that sense, being agnostic. And this definition of this distribution depends on a certain rewriting of the kth moment. Right? So we rewrote the kth moment as an expression in terms of this gamma map. And once you do that and you stare at that expression, you get the test. Right? It's kind of very natural. And this bypasses the Fourier requirement. Because again, in the Boolean world, to get such an equivalences between the Fourier side and the other side, you're using the duality, right? On one side you have Fourier coefficients, on the other side you have physical space quantities. So like for k equal to 2, that quantity, parseval and so on. Right? So this is kind of getting around that. So you can think of the gamma map as some sort of a dual object, mapping homomorphisms to their evaluations. But it's doing this purely without any reference to for analysis. So in particular, this is also giving you like a Fourier free proof of the Z2 case. Although again, it's kind of similar in that case. Right, and the analysis is just bounding this little gamma to the k, this constant. So once you fix the proof, the groups G and H, you just have to compute this quantity and see when is it bounded. Okay, and these were the results that we saw. The known results were these three families: Z2 to the n to Z2, Z3 to the n to ZP, and then Z2 to the n to Z2 to the n. Right? We can recover these. So again, of all these known results, we cannot recover the PFR case, but we can recover the maps to Z2 or ZP, and then we get like tests for this cyclic group characters, the linear characters of invertible matrices, and a bunch of tests for non-abelian groups. And all of this again is in the Hamming distance. It's kind of like, so there are some results when you do G to unitaries, but in the L2 sense. Okay, so that's all I have. Open problem, of course, is to like try to complete the picture. You know, can we hope for something as we have in the high soundness regime, like for all pairs G and H. And some hope is that because of this lifting and stuff, hopefully you can just prove it for finite simple groups or some of the basic elements and then build up. If we can try to use that. I did not speak about the randomness needed to sample this distribution. I just defined what the distribution is. Right? But you can then think about how many random bits are needed to sample from this distribution. Can you make that more efficient? And because these tests are higher query, like they are 3 query, 4 query, and so on, like for larger things, what would be a right notion of the random range? So for BLR tests, the classical thing you do is epsilon bias sets or an expander graph. Right? So what is like the correct pseudo-random notion for G to the K, from which you can sample this distribution more efficiently? And we saw one case of Lie algebras very briefly that it can also tackle such cases, but there it was via reduction to again the group case. But this kind of structure probably can be useful for other structured function classes, because that's where we can hope to get an exact expression for this kth moment. Right? So what would be other interesting domains to have such a framework for this? So yeah, that's all.